Welcome back to this course on digital systems, and in this introductory week I thought I should actually first of all take you back to some fundamentals of the analog computation that we had already done. Okay, the heart of this course is ultimately to do some digital computation, but we also should know what these digital what a digital computation means in terms of voltages. Okay, so for that we will look at the basic computation that we had looked at in this electronic system thinking course, right. So this is our V1, V2, R1 and R2. So we had studied in this electronic systems thinking course that this V out is some alpha times V1 plus 1 minus alpha times V2, where alpha is some function of the resistors and so on. So what this means is that if you have a time varying voltage like this, let us say it is a sinusoidal wave or something like that, okay, or even a distorted sine wave, let us say this is your V1 of t, right. We are saying that this expression holds for every time instant. Okay. So what we say is you take any time instant, okay, and you have a certain voltage which corresponds to this time instant t equal to t1. This is going to be V of t1. Okay. Similarly, you will have a V1 of t1 and V2 of t1, right. Then V naught of t1 is equal to alpha times V1 of t1 plus 1 minus alpha V2 of t2, right. But we had also studied in the electronic systems thinking course that in order to take this analog signal into the digital computer, we had to do two things. One is time sampling and the other is amplitude quantization, time quantization and amplitude quantization. So the idea there was to simply divide this time axis into some small sample instants where you are going to sample the data, okay, and the x of t now becomes x of nts, okay, where this is ts, the sampling time. Okay. Further, this was only time sampling, time quantization. Okay. But if you wanted to now do amplitude quantization, the x of nts, right, needs to be passed through what is known as the ADC, right, and this ADC would give you a quantized output for every time instant. So you give x, you will get xq as the output, which is determined by that staircase waveform that we had studied. So essentially you could have x of nts be a real number and xq of t be some integer, right. And we had actually also seen very briefly that this integer can be converted to a binary number. Okay. So for example, your x of nts would be some let us say 0.534 volts, but when you quantize this nts, okay, it could get quantized to 0.53 volts. The 4 is gone, you have lost that information, you quantize it to a certain bin and then you could assign a number to this bin, right. Please go back and watch that lecture if you need more clarity, right. you could assign a number, the bin number, to the quantized value. Okay. So therefore, what we were able to do was to take this time signal, okay, and convert it to a sequence of integers 0, 1, 3, 7, 9, back to 7, you know, something like this, depending on how fast you are sampling and what the quantized value for each of those values or each of those amplitude values were, right. So now what we said was, you can take this integer, okay, and convert it to a binary number, okay. So for example, 0, let's take 7, right. This can be converted to a binary number 111, 0111 for example. We will see how to do all this later, okay. And once you convert it to a binary number, your each bit can either be 0 or 1. This can be stored in a digital computer or it can be processed. You can do addition, multiplication, you can do whatever you want inside the digital computer, okay. So now the question really is, okay, this logic 0 and logic 1 are our ways of representing it. You know, it is a human representation of the exact data that we are trying to operate on. But the computer, the digital computer does not understand these representations, the 0, 1, true, false. For example, if I were to do logic operations, I could replace 0 by false, 1 by true. It is possible to do that, and the humans can process this, you know, true, false, +5, -5, anything you can call it, right, and it's possible to this thing. However, the digital computer, which is made of ICs, logic gates and transistors, as I told you, does not understand any of these representations. The digital computer only understands voltages, okay. So the key idea is, we need to first of all understand what does a voltage mean in the digital domain and what does it mean in the analog domain first of all, right. When we say, for example, let us say this was sampled to be 534 volt. What does it mean? It means that that number is 0.53 volts, 534 volts. It is not less, not greater. Okay, we were able to measure it only to that level, but to whatever level we have measured it, the analog value is exactly this number. There can be no deviation. If you add some noise, if you add a certain delta, 0.535, it's a different value from what we actually sampled. Okay, so that is a very, very important aspect for us to understand. So in the electronic systems thinking course, we had motivated that if you wanted to do any storage, then you had to go to the digital domain, okay. And we had briefly mentioned that digital computation is robust to noise, okay. Now noise is something that appears everywhere, appears in every single place, okay. So what happens if I am trying to do an analog computation and there is a small noise, okay. So let us say that our signal is swinging between 0 and 1 volt, okay. This is 0, this is 1 volt. Noise could typically be of the order of a couple of millivolt, okay. Now the problem is, let us say 0.53 volt, you added, so how much is this in millivolt? This is 534 millivolt. Now let us say there was a 20 millivolt noise on this signal because of some reason, okay. This will simply become 554 millivolt if it is a plus 20 millivolt, okay, with noise, with 20 millivolt noise. Now 554 millivolt is a very different value compared to 534 millivolt. Okay, and how different it is, it actually depends on, you know, how many bit ADC we are using and how many levels we are quantizing it to. Okay, let us say that the ADC step size was 5 millivolts. Okay, then 20 millivolt can correspond to 4 codes difference in the ADC output. Okay, if this, for example, if 534 millivolt when passed through the ADC gave you a code of a bin number of 72, right, then this will give you a bin number of 76, and therefore the two of them are very, very, very different. Okay, and if you compute the answer with this, you will get an incorrect result. Okay, and that is actually fundamentally the problem with analog computing. Okay, what we will see now is, once you take this analog signal, pass it through an ADC, and then binarize the number, right, and then you send it into a digital computer for processing, the processing is so immune to noise, right, that almost nothing can change the answer. Okay, I think that is the key point that I would like to highlight in this lecture and maybe the subsequent lectures. Okay, so let us say that I took this value, you know, I took this V1 of t, I sampled time quantized, amplitude quantized, and I converted to a sequence of numbers like this. Okay, I have to ensure, yes, there is no noise in this part when it is being converted and digitized, but let us say that I have been able to do that. I have got a sequence of numbers. Okay, and then I have digitized this number. So 7, for example, is 0, 1, 1, 1. Why? 2 power 0 plus 2 power 1, 2 power 2. You add these three, you will get 7. Okay, likewise 9 is going to be 1, 0, 0, 1. Why? 2 power 0 plus 2 power 3. Okay, we will come to how to do this later, but effectively it is, you know, you have a 1, 0 representation for every single integer that you have generated out of this process of sampling and time sampling and ADC, right, amplitude quantization. So now what we do is, I want to see what does this 0 and 1 mean in terms of voltages. Okay, that is the fundamental question that we are going to ask. What does 0 and 1 mean in terms of voltages? Okay. So for example, like I told you, I took the example of a simple inverter. You give 0, you will get 1. Okay, or you give 1, you will get 0. Okay, but again, this is a logical representation of this. This does not mean that 0 means 0 volts, 1 means 1 volt. Okay, so this is a fundamental point that we have to understand, right? So now let us go back and look at the experiment. If you remember, we had shown you an experiment on the voltage transfer characteristics of the inverter. What is the voltage transfer characteristics? It's basically, you take this inverter, okay, and I give V in and I get V out. Okay, remember, even though the input and the output have their own voltages, you have to give a supply to this inverter if this has to work correctly. Okay, that's because the transistors internally need their power, their current and all that. So you have a separate power supply that needs to be given to all these digital ICs if you want them to work correctly, right? So you give, so the idea of a voltage voltage characteristic, okay, VTC is a plot of V out versus V in terms of voltages, okay. Now V in, what is the range of V in? We assume that the input voltage to this digital inverter can be anything between 0 and VDD, okay, the supply. So for example, this in your ICs that you would use in the lab, it would be 5 volts, okay, or 3.3 volts, 1.8 volt. In the current chips in the microprocessor, the supply voltage goes down as low as 1 volt or even 0.7 volt and so on, right. So therefore, we assume that V in is going to go from 0 to VDD, okay, and I am going to plot V out versus V in, okay. So if you remember the experiment that we did with the 74XX series, right, the TTL gates, we got a transfer characteristics something like this, okay. In fact, whether you do it with CMOS, whether you do it with the TTL BJTs, it does not matter, all the transfer characteristics will look somewhat like this, okay. Now, so this is VDD, okay, and the input is going from 0 to VDD, right. Now the question really is, what is it that I can consider as a logic 0 and what is it that I can consider as a logic 1, okay. So the first obvious answer that would come to all our minds is logic 0 means you make it ground, 0 volts, okay. Logic 0, I would say I will call it 0 volt, logic 1 is 1 volt, okay, or not 1 volt, I would say VDD. It could be 5 volt, it could be 3.3 volt, whatever the supply voltage is for that technology and that IC, right. Now, so for example, this could be 5 volt, okay. Now the real question to ask, right, if you go back to our analog computation, right, what did we see in analog computation? In analog computation, we said 534 millivolt is 534 millivolt, right, or if the ADC bin size is plus 5 millivolt, right, then you could say anything between 530 and 535 is the same code, you will get the code 72 for that. So therefore, 530 to 535 millivolt, anything 5 millivolt this way that way, I will say is effectively the same voltage, right. That is what the ADC quantization tells us, okay. So the question here is 5 volt means logic 1, but what about 4.95 volt? What if I drop it by 50 millivolt? What if I drop it by 100 millivolt? Right? Remember in the analog computation, 100 millivolt with a 5 millivolt ADC step would mean 20 codes away. It's a different number altogether. We are now asking, what is this logic 1 in terms of voltages? Is it 1 voltage? Is it a range of voltage? What is it? Right? So, for this, we will also draw what is known as an ideal voltage transfer characteristic, right? So, what is the ideal voltage transfer characteristics that we want? We actually want it to be something like this. The ideal transfer characteristics should be something like this. Okay, this is VDD by 2. Okay. So, my input to this inverter can be anywhere between 0 and VDD, okay, 0 and 5 volt for example. But I have no reason to choose to favor 0 or 1. Therefore, I will just pick the middle voltage VDD by 2, and ideally I would want if the input is here, the input must be treated as a logic 0, okay. The output in that case should go to VDD, by the way, should go to logic 1, okay. Output in this region, right, if the input is in this region, this should be logic 1, okay. And if the input is in this region, that is VDD by 2 to VDD, then I want the input to be treated as a logic high, and therefore the output must be treated as a logic 0. This is what I ideally want, okay. So this is actually a very good starting point for us, because it gives us what is it that we want in practice, right. And therefore my first guess is it is not 0 volt, anything between 0 volt to VDD by 2, right. I want it to be logic 0, anything between VDD by 2 to VDD, I want the input to be treated as logic 1, and this is for V in. Okay. However, what we see is in practice it is not possible to achieve such a steep slope, right, or such a clear partition between logic 0 and logic 1, right. In fact, you see that when you plot the voltage transfer character in any technology, you will see that it deviates on the ideal curve and comes out to be something like this, right. This you cannot do anything about it, because these are the non-idealities of the transistors that are being used, okay. The transistor, we want to actually operate it as a switch, right, either it is on or off, that is what we mean by logic 1, logic 0, but it does not operate like that, and in the process you will get a very practical curve as shown in black here, okay.